Okay, so we discussed about two things or three things, right? For last class was first we said in the reservoir, right? So how first P has a function of the radius. Okay? And the first observation is that if we are talking about the radial reservoir or the radial well, okay, we say that it's very abrupt. Okay, if you plot the pressure versus the radius is very abrupt. You have a very strong drop in the region close to the wellbore, and we said for our case this was like 30 meters, okay, or 30 to 50, and then it was increasing but very slowly. So for production engineers, this is really the major contribution to the pressure drop. Okay, so we don't care too much what happens outside. That's very important for recovery, is very important for drainage, for many other things, but not for production, for productivity of the well. Then the second thing we did was to derive the ideal liquid IPR. Okay, we said at the end we end up with an expression like this. And I told you there was a guy called Millikan in the 1930s that he did some experiments on the field and actually saw that was the first time we got a straight line. And then people came and showed, well, if you do the equation, actually you also find a straight line. Okay? And the last thing we did yesterday was we said, if you want to include the effect of this damage, okay, or if you want to include some other effects that we are not going to discuss here in class, but some non-ideal effects, some heterogeneity, some close to the damage, wellbore damage. Okay. You sometimes use a factor called S, that the main effect, you see that is in the J, in the expression of the J. J is KH over 1843, BO, MO, LAN, RE, RW, 0.75 plus S, right? So S, if it's positive, it means that is making the lower part of the J bigger, thus the J becomes smaller. You have less productivity. So this is damage, usually. Okay, we call it flow impairment, something that impedes flow. If it's zero, it's just ideal well. And if it's negative, it means stimulated. Because you're making the lower part smaller and then J becomes bigger. And remember, we have a limit to that number. We can improve, but physically, we have, remember that number was, for our case, like 8.5 minus 0.75. So S maximum we can get is very close to 7, okay, with stimulation. Not sure why this came so. Okay, so today, the menu for today, we're going to look at gas, okay? And first, I want to make a comment for liquid. So, an assumption okay, so an assumption we used previously is that, if you remember, we had an integral, right? We had an integral from PWF to from PWF to PR of 1 over mu BO dP, right? When we were deriving this IPR. That was the integral that we had. And one assumption we made, if it's ideal liquids, then we said 1 over mu BO is basically a constant. Okay? But in reality, it's not exactly like that. And we are going to see it's not exactly for real, let's call it here real oil. Okay? And we are going to look like how these two variables look like. So if you plot viscosity of the oil versus pressure, okay, at reservoir pressure constant, okay, you get the following behavior. You see that it goes down with pressure until it reaches certain point, which is the bubble point pressure. If I go above that pressure, I will have just one phase. Okay, so here I have oil and gas, and if I go above this point, I have only oil. Okay, and from this point, it will start to go up. Okay, while for the BO, you have a similar behavior, but exactly the opposite. That is going up, and then you reach this bubble point, PB, and then it starts going down, not so, something like that. Okay? So here, like the explanation in a way, is that, remember what is BO, right? BO is Q oil at pressure and temperature divided by Q oil at standard conditions. Yes? So the oil, when you start increasing the pressure, it has more gas in solution. Okay, like gas will start to dissolve into the oil and make it more light. Okay, and when the oil has a lot of light components, it will tend to be more compressible. Okay, it will tend to squeeze more, to change its volume even more. So that's why it's increasing up to that point. Now, when I have pure oil, this line here, which is actually not so much, but let's make it. We are going to see this later in detail when we talk about black oil properties, okay? But it's just to tell you that's how it behaves, two things with pressure, and then you have an inflection point where it changed trend, okay? Here you have single phase oil, but that's just the compressibility, okay? Any liquid has some compressibility. Even if it's oil and always will be oil, if I compress it, I will have a slight change in volume, okay? Not very much, but I'm going to have a change in volume. Also in water. Okay, so if I have like a tank, okay, and I put in this tank a piston, okay, and I fill it with water or I fill it with some liquid, okay, and I place an elephant or someone on top, it's going to slightly, okay, it's going to slightly change its height, the volume. Not much, but it's going to compress slightly. Okay, so in reality it does that. So really I cannot take it so simple out of the integral for real oil. Okay, so for real oil I have to find an expression for PWF and PR. Okay, this guy that I just assumed it was constant before. But when you plot the 1 over, when you plot versus pressure from PR to PWF, one over mu BO, you see that they have actually opposite trends. If you see here, one is going down and the other is going up. Okay, so when you are from that point, this one is going down and this one is going up. So that makes that it always has the same trend with pressure, which is going like that. Okay, it's just a straight line. Even though they are changing, the viscosity and the VO by itself, they are changing in the opposite directions. So that makes it that it will be constant. Okay. So how do you integrate a constant function? Hmm? Well, not constant, but linear. Okay, a linear function. Yeah, the coefficient, the slope. Okay, so in that case, so to evaluate that integral, we normally use this integral of PWF to PR 1 over mu BO dP will be equal to a linear function, which is P evaluated in PWF and PR, okay, times this constant, which is BO average. Okay, evaluating at an average, P average at an average. And this P average will be PWF plus PR divided by 2. Okay? And that gives you the expression that we already know, PR minus PWF, 1 over mu BO. But now be careful, they are not constant, but they are average. Okay? So that's the only change you have when you use a real oil. Okay? You don't assume that is constant, but you just evaluate the multiplication of both at an average pressure. And of course, if you, let's say that you are, okay, this is QO, right, and PWF. That's the equation of the IPR. So what will happen with time? Okay, let's say that you are operating at a constant PWF. Okay, somehow you're keeping the bottom hole pressure constant. Okay, so what's going to happen with time? The pressure, reservoir pressure is going to drop, right? So how does it drop in the IPR? How does it look like? So this is for PR1, then you have PR2, right? And then you have PR3 and so forth. Okay, so you see, even the bottom hole pressure doesn't change. Okay, I'm always producing with the same PWF. Okay, but the reservoir pressure is changing, and that causes the P average to be changing in each one of them, because P average 1 will be PR1 plus PWF divided by 2, while P average 2 will be PR2 plus PWF divided by 2. Okay, so when we are talking about the real oil, we have really to update these two factors with time, okay, with reservoir pressure. Or if you're changing bottom hole pressure, you also have to update. Okay, so let me write here just for clarity, just for you have it in your notes. So for real oil, you have to use the expression that Q oil will be KH PR minus PWF 18.43 mu BO evaluated at P average, okay, times the ln of RE RW plus 0.75 minus 0.75, okay, plus S. Okay, which is very similar for ideal liquid. Okay, I'm just using this one I have to evaluate now at P average. Okay, now let's go to gas. Okay, let's see what happens with gas. Okay, and if you remember, we start with the same equation that was Q over 2. If you remember, Q gas divided by area will be K divided by viscosity of the gas dP dr. Okay. And then we said that the area was 2 pi RH. Okay, and then I introduce it here. Qg, Q pi RH. What was the next step? If you remember, the next step that we did with the oil was the local rate, right? We converted in terms of the standard condition rate, right? If we remember with the oil, we said Q oil is BO times Q oil. That's why we ended up with the BO in the equation. So with gas, we are going to do exactly the same. Q gas equal to BG times QG. Okay, so let's try that. This will be, sorry, this shouldn't have the hat. Okay, it's just QG because it's local. When I don't use the hat, it's local rate. Okay, it's at that pressure and temperature. QG BG 2 pi R H K over dP dr. Okay. Now I move everything that has to do with pressure on one side to the right side, everything that has to do with radius on the other side. Qg is a constant, so I can leave it here. 2 pi is also constant. H is also a constant. K is also a constant. Actually, I can move them here so it looks nicer, the equation. And here we have Bg, mu g, and dP. Okay, and here we have dr over r. Okay, I'm moving everything that has to do with radius on the left and everything that has to do, so actually this Qg should also be someplace here. Okay, because it's that's all of that here is a constant. Now we know that Bg depends on pressure, right? What is the definition of Bg, if you remember? Is Bg is, yeah, that Q, but how do you express in terms of the equation of state, right? Because we said this is a volume at P and T, okay, divided by a volume at standard conditions, okay? And the volume we can express as that we have done on Tuesday, I think, right? How we calculated Bg. We said, yeah, I think the way we did it was we said Qg times density of G will be Qg density of G. That's the way I think we have derived it. And then we end up with Qg over Qg will be density of the gas over density of the gas, and here we end up with it was P over standard conditions over R set standard conditions and T standard conditions, and P R set T, right? I think so. You have to check. Can somebody check your notes? If well, I can do it here very quickly. It was day 2. or maybe day 1. I think it was day 1. Yeah, it's here, and then we have used the ideal gas law, and we ended up with Bg being equal to, okay, P standard conditions divided by T standard conditions, then T and P set. T and P set, okay? So we ended up exactly what I found here. P standard conditions, T standard conditions, P and set T. Okay? So that's my BG. That's the definition of BG. So you see it depends on pressure. So I come here and I substitute the definition of BG here and I put the snakes. So here I'm going to make the snake between, if you remember, the solution of that was ln of R evaluated between RW, well bore, right? And then the other bound was, yeah, RE, but we are saying we are going to do it up to reservoir pressure. And reservoir pressure occurs for pseudo steady state where? If you remember, last class, 0.47 RE, right? 0.47 RE. That is, I told you, if you stick a needle in the reservoir exactly at 0.47 RE, you will find reservoir pressure. Okay, but we cannot do that. But if you could, so that would be equal to a constant 2 pi hk over qg, and then the integral from PWF, the pressure at this radius, and the pressure at this radius, which is PR. And here we have inside viscosity of the gas, and Bg is 1 over Bg, so we have P over Z T dP. Okay? Yes, I think so. You have to check that I'm not doing any mistakes. Bg. Let's see. Okay? However, how is temperature in the reservoir? How is temperature in the reservoir? It's constant, right? It's constant with radius. If I go and measure temperature, at any radius in the reservoir, okay, I come measure temperature here, 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 it will be the same. Okay, it's uniform temperature. So in that case, this guy becomes a constant and comes out of the equation. So I'm going to have here is ln of RW minus 0.75. Okay, and I can add the skin if you want. Okay. Then I have 2 pi hk over qg. Actually, let's do something. Let's rearrange the equation, okay? Because the equation we want usually to have it explicit in terms of rate. So I want to move this guy. This guy down here. Okay, I want to move QG here. And I have here reservoir. Oh, but I'm missing also these two guys. Okay, I'm missing here PSC will be here, and TSC. So I have TR, TSC, PSC, and I have finally PWF, PR, P over Z mu G dP. Okay, I think so. You are the ones that have to be checking if I'm doing everything good. TRP. Yeah, it looks fine. Okay. So now I have a problem. Okay, before I could say, well, these properties for ideal liquid or for oil, I know it will behave like a straight line or they will be constant, but here I don't really know what happens, okay, with that integral. And I have to make the integral between PWF and PR. Okay. So if you plot, okay, we are going to do the same that we have done for oil. If you plot this factor, Z, and the viscosity of the gas versus pressure, okay, you obtain a very interesting behavior, okay? First, you obtain like a straight line region, okay? Then you obtain some curvature, okay? And then you obtain a relatively constant region. If you go and do experiments, you plot pressure, this is a T equal TR constant, okay? You find that behavior. And then we can define three regions, okay, for which I want to apply my equation. So this region from P star and down, that is what we call the low pressure region. Okay. Then I have this region where I have a curvature of this P over Z me. That is what I'm going to call the medium pressure region. And from this point on, this is the high pressure region. And in all of them, you can do some assumption. Okay, so let's look first at the low pressure region. Let's put it here. Okay, for low pressure, okay, then I want to make this integral, to evaluate this integral, P over Z me dP. Okay, and we said it's a straight line, right? So how should it look like if I make the integral? If it's a straight line, it means that P, this is a constant, Z and me, right? Yes? Okay, so what happens when I integrate? 1 over Z me, this is going to be now a constant, okay? And the integral, it will be P squared, okay, divided by 2. Yes, evaluate it in PWF and PR, and this gives you PR squared minus PWF squared, okay, divided by 2. Okay, C me. Where do I evaluate the C and me? Where do I evaluate? These are two properties, right? Like the set, you know, you use this calculator. At which pressure and temperature do I evaluate this set? It's constant, so it doesn't matter. I can do it at bottom hole, I can do it on reservoir, as long as my pressure, if P, R, and PWF are in the low pressure region. Okay? Both are in the low pressure. So it's constant. It doesn't matter which pressure I use. I could use PWF, I could use PR, I could use P average. It doesn't matter. Okay? So here you evaluate at any pressure. It should give you the same result. Okay? Now let's substitute that in the equation we had in this equation. Okay? So what we end up with is, yes? At one specific time. Remember, time is not here in the picture. Time enters, this is pseudo steady state, so by changing reservoir pressure is the way I'm accounting for time. Okay, reservoir pressure is changing with time. Okay, but that we don't care. You're not in production, you're not in reservoir. If you want to see how this PR change with time, you go to reservoir engineer. Production, we say that reservoir pressure we measure. We shut in the well and we measure reservoir pressure. Okay. So let's see. Q, we have 2 pi k h ln of r dot re. And here you have to pay close attention. Here we have TR. What else did we have? T surface condition, P surface condition. And now the solution of this integral will be 1 over mi z, okay, divided by 2 PR squared minus PWF squared. Does it sound familiar, that equation? Or not really? What equation did we use when we applied our equilibrium some time ago, right? This week. You remember what was the back pressure equation that we used? No? It was something like this. If you remember, CR PR minus PWF squared to the power of n, right? That was the equation we used to represent the inflow, okay? And you see, it's almost exactly the same as this equation. The only thing is that n is equal to 1. And why is that? When would we say, do we have n equal to 1? Darcy flow, yeah? And this is the assumption we are using. We are departing from Darcy equation, from this equation, which is linear, and it means it's Darcy, okay? So these two are exactly the same. If n equal 1, that means Darcy flow. Okay, so from the theory, once more, this equation that we have here, that was measured by, I don't remember the name, but by the United States Bureau of Mines, they were measuring in the field and they found that equation empirically, and now you come on the theory and you see, oh, it looks exactly the same. Okay, which is very, very, very nice. So this 2 goes away with that 2. Okay, and yeah, and that's the final equation we have for low pressure. If you remember, for low pressure. Now, what happens for high pressure? Let's keep, this range, which is you're going to do it now very soon, okay? We are going to work on an exercise on this range, which is every time you have something, a curvature, it means non-linear, it means pain, okay? Difficult for us. But this line, we can integrate. We know how to integrate lines, and we know how to integrate a constant, right? How do we integrate a constant? Just wait here, think. Okay, so for high pressure, let's say for high pressure, and that means that both PWF and PR are in the high pressure region. Okay, the high pressure region that we said here. Okay. Then we know it's a constant. So the integral of P over me Z dP from PWF to PR, if this guy is a constant, what happens? It comes out of the integral, right? So I have P, me, C, and I can evaluate at which pressure do I evaluate? Any pressure, okay? It doesn't matter if I do it at PWF, if I do it at PR. So let's say we evaluate at PR, okay? Just to, and then we have PR minus PWF. Now we go back again and we substitute on the full IPR equation. QG would be 2 pi kh divided by ln of R E RW TSC TR PSC, and we now say PR over me C, okay, evaluated at PR, and we have now PR minus PWF. What does it look like, that equation? All of this is a constant, okay? Sorry, not up to there, but all of this is a constant, okay? So it looks like a liquid IPR. If you remember, the liquid IPR was Q oil JPR minus PWF. It's exactly the same expression for gas. So the conclusion we reach is for high pressure gas, it behaves very similar to a liquid. Okay? The deliverability of the well will be like a liquid. That clear? Yeah. We're going to have an exercise, so try to stay awake for some more minutes, and we are going to have an exercise to wake you up. Okay. Now we come to the most complicated part, okay, which is this integral. Okay, which we say now we are in the medium pressure range. Okay, and here the integral of P me Z. Okay. We have no choice but to get either data from the lab or to use an equation or to use something and integrate. We have no other solution. Okay, so it goes like this linear, then you have this curvature, and then it goes like that, pressure, and this is P over me Z. We have no chance but to integrate. Okay, to integrate numerically this. Okay, but instead of, so let's say we have here, right, this is PWF and this is PR. The integral, what is the integral in this figure? Is the area under this curve, right? So we are basically calculating that area. Now, every field and every well, they will have different PWF and PR, are going to have different. So the integral will be different. That's something that it's a bit, because you have to perform that integral every case for every pressure that you have from here to here. And that might be very tedious. Okay? So what is another way to calculate this integral? An alternative way. Trapezoidal, yes, but that's how I make the integral. Okay, I can do like that, can apply the trapezoidal rule, or if you remember, probably your classes also with Kalashnikov, we should have him here for support, okay, in case I make mistakes, so he's correcting. The integral of that is also equal to this integral, right, from 0 or from P standard conditions, okay, minus the integral of this region. Yes? Minus. Here there is a big minus. So instead of changing the bounds for every P and F, what I'm going to do, I'm going to make the integral from P standard conditions or any pressure, arbitrary pressure, from here to here and from here to here, and I'm going to subtract them. And that's going to give me this integral. Yeah? So in that case, I don't care. I don't have to be making that integral for every, from PWF, let's say it's 80 and this is 300, or now I have 70 and 300. Okay, I have to perform it for every case. Here I pre-compute this integral. Okay, I make a table, and this is what I call, this is called the M function. Okay, M function is basically M, depending on P, is the integral from P standard conditions to P, to a given P, set dp. Okay, that's the M function. Okay, and I have a two. So I have, also please note that the M function usually includes these two that I have here. Okay, these two that go there. So I'm using this M function. So that means that the integral of PWF to PR of P divided by me set dp 2 is equal to the integral between P standard conditions to PWF P me C dp plus, sorry, this one will be minus, this one will be plus, to P standard conditions PR P me C dp. And that's equal to M at PWF plus M at PR. Okay? So from the data in the lab, from any model that I have, I tell the guy, please make a table. Okay? Make a table of M, generate this table. For every P, generate a table of MP, okay, integrating for different pressures, P1, P2, P3, and so forth. Okay? And then if I want my this integral, which goes into my IPR, okay, I just have to subtract the M for reservoir pressure minus the M for bottom hole pressure, without actually doing the integral. I just have to have pre-tabulated this M function. So at the end, the IPR equation ends up being QG pi KH T standard conditions over P standard conditions, I think it's reservoir temperature, ln RE RW plus S. And here I have M for PR minus M for PWF. Okay, I think, let's see, let's verify once more. Okay, so that's the IPR for medium pressure. For actually, it's valid for all pressures. Okay, it's not valid for, it's valid for all pressures. But if I'm exactly in that range that I have the medium pressure, where it's not linear and when it's not constant, I have to use this equation, this M, which looks nothing like liquid IPR, empirical IPR, doesn't look like anything. So now let's do an exercise, and the exercise we are going to plot. So we are going to first assume low pressure, okay, and we're going to use the IPR for low pressure. And then we're going to use this equation with M, okay? We're going to use MP, okay? And we're going to calculate the IPR for all pressures. And we're going to see how different they are, okay? So for that, let's go to this exercise. I think that's an exercise to deliver. So it should be, it's exercise 4. Yes? The RE, the 0.47. Yeah, let's go back to the class of yesterday. Okay, if you remember, we said we want to integrate, right? We said we want to integrate this equation from bottom hole pressure, okay, from the region close to the wellbore, all the way out, okay? But we have to choose to where, to which point we are going to integrate. And one variable which is very useful is average pressure, average reservoir pressure. That's something I can measure. I shut in the well, I leave everything to balance out, and I'm going to reach that pressure. So that's a pressure I can measure in the field. I shut in and I measure. Now, what I told you here is that there are two ways. One of them is if I have a constant pressure at the bound, okay? Somehow I have an aquifer, I have an injector. The reservoir pressure, if you do it mathematically, reservoir pressure, we are not going to do it here in class, will be exactly if I go at 0.61 the external radius. And if you want the demonstration, I can give it to you, but just trust me, it comes from God, let's say, and 0.61, if you stick a needle there, you will measure reservoir pressure, okay? And if you have no flow, okay, which is a pseudo steady state, then the reservoir pressure occurs at 0.47. Okay, and that's very convenient because now you can apply that expression and you integrate between wellbore radius and reservoir pressure. Okay, so because if you have now the position where reservoir pressure occurs, you just can substitute it here. Okay, so let's see. Let's open that exercise for our well. Okay, and you see we have 4 columns. Okay, so we have first the low pressure IPR that we are going to plot. Okay, just to see how it looks like using the equation, the low pressure IPR equation, which is this one. Okay, that's low pressure. So if you click punch Alt F11, you should have it in your equations. IPR gas, you see IPR low pressure gas, QG. And you have P squared minus PWF squared. And you see you have a constant, and that's because this equation that I derived here is in SI units. But if now I want to use bar, and I want this to give me standard cubic meter per day, I have to do some manipulation. Okay, I have to take out a constant. So that's that constant here. The IPR of any pressure, okay, or medium pressure, it's using this M. Okay, so I need the M at reservoir pressure and the M at PWF. And this M is calculated for you here, M function, and here basically you're doing that integration. Okay, you're integrating between P standard condition 101325 to the pressure that you specify here. Okay, so let's start to plot IPR. We know bottom hole pressure can be between reservoir pressure and down, right? So let's put the first number will be reservoir pressure. Okay, and the second number, let's go in steps of, let's say 30 maybe. I think that will be too much. Let's say 50, 250, 200, and so forth. Okay, the low pressure equation, we come and we look for IPR in user defined. IPR, it has to be low pressure, LP. IPR LP gas, QG. And here we start populating numbers. KH is here, okay, and that I have to block. T, reservoir pressure, reservoir temperature is here, and that I have to block. Set, where do I have to evaluate this set?
What is the unit of temperature?
Kelvin. It will be Kelvin. It has to be absolute because it comes from the real gas equation. Now, where should is this set good enough? This evaluated at reservoir pressure and temperature. What did we say when we derived the low pressure equation? We said that this was a straight line, right? This function is a straight line. Therefore, this is a constant set over me. So it doesn't matter where I evaluate. If it's at the bottom hole, if it's a WF, PR, it should give me the same. Okay? So here I have set at reservoir pressure, and I have viscosity also at the same pressure. So I can use those two. Set, I block it, and viscosity here, and I block it. RE, external radius of the well, 450, block it. RW, I have it here and I block it. The skin factor, in that case it determines the well is damaged and it has a factor of 3, block it. Reservoir pressure is this guy here, right? The first, or let's take it from here, reservoir pressure, I also block it. PWF is the value to the left. Okay, so let's just verify. KH, it's B11, and that has to be frozen. T, B3, and that has to be frozen. Set, B4, and here we have to be careful. We know that the product of me and C, viscosity and deviation, it will be constant, but they have to be evaluated at the same pressure. So I check here, this set is at reservoir pressure, and this viscosity is also at reservoir pressure. So I can use those two, B3 and B4, B4 and B6. RE, it's radius, external radius that has to be blocked. Wellbore 0.11, S is 3, and PR B2 and PWF 303. Did you get similar numbers? Yeah. Okay. And the beauty of that equation is that, let's say you are designing a field. Okay. The beauty of this equation. So why if we can measure? Okay. Why do we use expressions like that? Okay. Well, for once, it's useful when you don't have any well. Okay. When you're just in the planning phase, you want to have an estimate how much your well will produce. It's useful if you predict it and then you measure it. You see you have a deviation, and you can start to find out what is the reason. It's because my permeability might be lower than what I thought initially. It's because I might have damage. It's because my fluids might be different. So it's good for troubleshooting. And the last thing is also useful for future performance. Okay, you want to know how much you will produce, let's say in 10 years from now, from that well. So you can use that equation to predict future performance, okay, because the well is not depleted yet.
Why low pressure? Why low pressure?
Low pressure, we're just using that, okay, just to see how it, and you should have an equation like that, okay. And now we are going to compare if we use the M, okay, if we use the real pressure to see.
I just want to understand why the low pressure, the name, what is the meaning?
Well, low pressure, what we just mentioned here, this function P over mu C is linear in the low pressure regime. Okay, so when it's linear, I can just simply integrate and find that equation, and it's much simpler to use. Okay, but you're going to see the difference with the other equation. If the difference is significant, then you cannot use it. You're going to get a big deviation.
What is the range for low pressure?
I think low pressure is down to maybe 120 bar, something like that. From 100, yeah, it's like 80 to 120 bar.
Are we going to use another equation to compare?
Yeah. Okay, so that's the second, the 2 second. Okay, this one was the low pressure IPR, looks like that, and then we are going to compute the M, that is the real IPR, and see how different they are. If they are the same, it means that I can use the low pressure, which is much easier. Okay, it's much easier to use. If not, I have to go and calculate this M function. Okay, the M function, let's see, how did I call it? It's called M function, simply. Takes pressure, temperature in Celsius, be careful, and specific gravity. Okay, so let's say M function. Okay, pressure. Which pressure do we have to take here? This one? Okay, that's correct. Then temperature has to be in Celsius, so I have to take this guy and subtract 273.15, and I have to block it. And the specific gravity of the gas, which is 0.8, and that I have to block also. Okay, because I cannot go all the way to 1, so let's use 1,0,1,325. Okay. Well, let's use 5 maybe. No? Well, that's not really so important. But why not? 7. It works? Okay. Yeah. In theory, you're not going to run if you lose at such a low pressure, probably you have a low pressure equation. Okay. So I'm not sure why this is giving trouble. Okay. So I have the M function, and then I have to use the IPR for the medium pressure, which is IPR P gas, okay, is this equation that is using M, okay? And be careful, it will use M for reservoir pressure and the M for the current flowing bottom hole pressure. So let's use that equation, IPR PP gas, and we have to populate once more, okay? KH is this guy, block it. Temperature is this guy, block it. External radius is this guy, block it. Wellbore radius, this guy, block it. S3, block it. Okay, and here we have to be careful. M. The M function of reservoir pressure is this guy, okay? And we have to block it because you're always you have the same reservoir pressure, okay? What you're going to change is the bottom hole pressure. So the M function of reservoir pressure will be fixed, and what you're going to be changing is the M of the bottom hole pressure. Okay, and in this case, both of them are the same. So it gives you 0 rate, and then I drag down, okay, and I obtain some numbers. Do you get similar numbers? Yep. Okay, and you see the difference between them. And actually the difference is quite significant. Here, if you're working at low rates, they give you basically the same, because the two curves, they depart from the same place. Okay, so that's where you have the smallest deviation. But if you move here to operating pressure 150 and 100, you see the difference is significant between the rate, okay, between these two equations. Okay? This one?
Yeah. Okay, no. So that linear profile that you explained can only be verified from the wellbore pressure up to 250 based on the chart.
If let's say, maybe we can try, I'm not sure if it will damage the, well, yeah, because this set will change, I think.
Based on the chart or not?
On which chart? This one?
Yeah, because I saw that from 300 up to 250, it's quite the same. So isn't that what we are comparing?
No. Because this is high pressure, so
yeah. Oh, okay.
Yeah, in high pressure we should use basically the linear. You see, it's like a linear equation for high pressure, the IPR.
Okay, but could you go for the explanation of the notes?
Yep.
Yeah, that thing that you explained here. And this is for the beginning. This is for the lower pressures.
We are now someplace, our range of pressure is someplace here. Okay, so we are actually covering the whole range. If our reservoir pressure and bottom hole pressures were in this range, okay, they will be basically linear. Okay, very close to linear. If they were in this range, both of them will be exactly the same. Okay, but because we are in this range, you cannot use the low pressure equation for that range. Okay, so if we want to, let's see, I hope I don't make, okay, let's see if we had reservoir pressure 120. Don't do it, I will take the risk. Okay, and then I say 110, and then I drag it down. Okay, you see that the two equations, they become very close.
Yeah.
When now, because now reservoir pressure is 120, and that's much closer to this region where the two of them are constant. So the two equations, they look pretty much alike. Okay. If we go even lower, if we use a pressure of maybe 80 bar, okay, they are going to look even closer. 980. Okay. We got a negative number for some reason there.
You put 89, 80.
Oh, okay. So it will be 75, 70. Okay, you see that they go very close to each other. Okay? And that's because the 2 points, remember, the 2 points, bottom hole pressure and reservoir pressure, has to be in that region. If one of them is here and the other is here, you have to use M function. If the two are very high, then I can use this linear equation. Okay? So I think that was, let's copy that. The pressure was 304, right?
Yes.
3 what? 303. Okay, and we started with 250. This will be 200. Okay, and 7 because we cannot go that low. And here you have a significant difference. So if when you're planning your well, you use the red equation, then you're going to get a good surprise, right? When you start producing, you say, wow, I get more rate. But if you do the opposite, okay, if you do use this curve, and then in reality you're producing here, it's you're going to be fired, yes.
What is the best approach?
Well, the most general approach is to use the M function. But it takes more job to because you have to get this table. Okay, you have to do that. You have to get this table. You can get it from lab, but it costs some money. Okay, but that's the most general approach. But usually, if you are below 100 bar, it's okay to use the squared the low pressure equation. I guess for your fields here in Mozambique, you will have to use M, or you have to use the high pressure equation because you have relatively high pressure. Okay, so here we can say we can make a note. Okay, there is a significant difference between the IPRs. And remember, this red one is saying C, here QG is CR, PR squared minus PWF squared. Okay? While here, this one QG is a constant times M PR minus M PWF. Okay? While if we use, I just want to copy and make that, that's not something you have to deliver, it's just to show you. What did we use, 80 or 80, and then now we use here 75, 70, 60, I need one more point, 55. Okay, you see that they become very, very close for low pressure. Now, I suggest, so let's paste that here. Again, here, for low pressures, that means P below 100 bar, typically. PWF and PR. Okay, both pressures has to be lower than PWF. Both curves are very similar. Okay, there is not much difference between the curves.
For high pressure, there is another equation.
Huh?
For high pressure.
High pressure is constant. Remember, high pressure, the equation was like the oil equation. Okay, you have a C times PR minus PWF. Okay, and that means in this range here, if you're talking about high pressure, it's just a straight line. Okay, so
what is the lower limit for us to consider high pressure? Or the range?
Yeah, that is in the book of Michael Golan. You know, he might come to teach next semester, so you might be lucky that he. Let's see. Don't tell him that I have. Let me just do something. Just assume, and you can find it in his book. So for pressures below 1,000 psi, which is like a bit less than 100 bar, you have linear. For all the rest, you have to use M function, and then for this range is relatively constant, more than 4,000 psi, and that's how much? How much is 4,000 psi? 275. Okay, so if both reservoir pressure and bottom hole pressure are close to 275 or above 275, then I can use the liquid, like a liquid type IPR. Okay, that clear? So we solved the exercise. That's a bit cheating, but I hope you also should try to do it again to try to understand it more deeply. Okay, we now have the menu for today. We have choke. Okay, so should we take a break first? Let's say 15 minutes. Okay, and then we go and talk about choke, which is very interesting topic. Okay. We have one more IPR to cover, which is, wow, that was a lot of writing in only too much, okay? Yeah. So there is one more IPR that we have to discuss, which is for when you have two phases. We have discussed pure liquid, we have discussed pure gas, and now we have to also touch a bit about two-phase. Two-phase is a mess. Okay, you have the properties of the oil, the properties of the gas, and also you have the permeability so far. We are not integrating it because it's just you have one phase, so it doesn't change. You don't have like the amount of oil or gas is the same always. But when you have two phases, the saturation changes also. Like in some parts of the well, you have more gas and then the gas flows easily. And some parts you have more oil and then the oil flows easily. So that has to come inside the integral. So that's really a problem, a mess, and there is not really a good way to predict IPR. So I'm going to I'm going to talk a little bit about it, but that will be when we talk about multi-phase flow. Okay, we're going to talk about the most used equation that is called Vogon Equation. Have you heard of it? Vogon? Vogon Equation? No? Okay. So that equation is used for when you have two phases. You have gas and oil. Okay, so choke. The choke is a very important element in the system because it's used to control and regulate production. Okay, to control and regulate production is critical, okay, because that's the only way we have to control the well. And we have two types. One of them is fixed opening, okay, sometimes called positive choke, also called bean choke, okay, and you have adjustable choke. And if you remember the exercise we have done, I think was on day 1, long time ago. I hope you remember. Okay, we had this was not here, maybe it was day 2. Okay, we were doing wellhead equilibrium, and we were saying what happens if you want to produce 1.5 million. Okay, so then you have to put a choke between the separator and the wellhead to cover that. And the choke, its the main function is to bring down the energy, okay, to dissipate energy. So that's why it's a very aggressive environment for the choke, because it has to burn a lot of energy very quickly. So let me show you how it looks like, a choke. So that's one type, adjustable. Okay, so that's a bean choke. That's also from the book of Mike, from Golan. Don't tell him. Okay. And this type of choke, fixed opening, it means that you cannot regulate, you cannot open or close. Okay, that's only to restrict the flow such that you don't pass certain limit. Okay, let's say if you pass certain rate, you might have sand production, you might damage your well, you might have too much erosion. So they put this bean. Okay, that's the insert. It's an insert. Okay, of course, you close the master valve, close everything, depressurize the system, and then you open this screw here, you take it out, you unscrew the beam, and you take it out. Okay, and you change with a different size. With the life of when the pressure starts to decline, if you want to maintain the same rate, you have to put a bigger choke, okay, a bigger diameter. Diameters of this choke, or the size, comes given in increments of 1/64. inch. 64 inch. Okay? Starting from like 1/8 of an inch, which is extremely small, all the way, I think the maximum is around 2 inch. Okay? So 1/8 plus 1/64, 1/8 plus 2/64, and so forth. Okay? And the diameter is basically this diameter of the throat. Please note that is very different from an orifice plate. If you have, okay, in an orifice plate is something like that, okay? So you lose pressure, you reduce pressure here, but then you recover it very quickly. Where you have all of these losses, the channel is very narrow, so you have almost no losses. You have loss and then you have immediately recovery. In the case of a choke, that section is very long. Don't remember now the length. Okay, such that in that region you have a lot of losses, and then when you expand again, you cannot recover these losses. There you can recover very little of it. Okay, there are some other types which are adjustable choke. So if you are adjustable, so if you are a poor boy, you have a poor well, and you are doing poor operations, you use bean choke. Okay, but if you're a rich guy in the North Sea or in Coral Field and you want to control your wells, then you use an adjustable choke, because you don't want to send someone every day or every month to come and change this bean. Okay, especially if you have many wells or if your wells produce a lot. Okay, if they give you a lot of revenue, then you can pay for an adjustable choke. Okay, and the adjustable choke, we have different models. Okay, one of them is this model that we discussed previously, okay, which is like this type, and that's called a needle choke. Okay, there is another type called Willis type choke. That's the figure I'm going to show here. That's something also called Rotary Disc. Okay, that's also something people are not using it so much now, but you can find it in the field. So it looks like that. Yeah, let me put it maybe on another page and then I pull it back up.
The only difference between these two types of chokes, the beam and the adjustable, when it comes down to mainly
Well, cost, and that you can regulate, that you can change the opening. Okay. On this one, you can change by changing the position of the needle. You can regulate how much delta P you have. Okay, which is very practical. You come here and you move up and down, and then you change the rate. Here, you have to close your well, shut in production, depressurize, and then you have to change that choke. Or you might also place some chokes in parallel. Okay, you might have a battery of chokes, which is not so common. But if you have the stream from the well, you might have here a choke, which is very big, and after that you have a valve here, where you have another choke. Okay, so you have two chokes in parallel, so that avoids having downtime. Okay, if not, that's a very fairly quick operation to change the beam. Okay, so that's another type which is very common. Probably you will find it in the field if you go to any field here. Okay, where you see here you have two discs, the fluid comes through here, and when the two holes, the discs, they have two holes. Okay, when these two holes are aligned, the pressure drop is minimal. Okay, I'm having like almost unrestricted flow. But then I can start rotate the two discs, one with respect to the other. Okay, and the holes, they become misaligned. Okay, when I have like that, I have no flow. okay, because they are not aligned at all. So this will just looks at the wall. Okay, when you have this one here, the area in between is where actually you have the flow here. Okay, so that's how you regulate by putting one in front of the other or changing it. That's how you regulate the pressure drop. Very clever design. And we have one, by the way, in our university. So let me show you. I think I have a picture. You know, we have now a trend that is you want to take everything digital. Everything digital, nothing, no. So people are throwing books, everything. Okay, we want to have everything on the computer, which is nice, but then you have to argue that you want to keep this big guy because you want to show how a choke looks like. It's very different if you see a picture and then you try to lift the guy and it's extremely heavy. You almost break your back because it's impossible to move. Okay, this is a 10,000 psi choke. The fluid enters through here, and here you have, when you rotate this handle, you actually move. One disc is fixed and the other disc rotates. Okay, so that's how you change the choke, the delta P. Okay, and there is one more type of choke that I want to show you, and that I'm not sure I have the picture. Chokes. Not sure if it's this one. Okay, it's like that, but there is a better case here. Not this one. Okay, it's something like that. Okay, where you move. So you have one cylinder inside the other. Okay, and that cylinder, one has holes and the other has also holes. So when one it's let me go back to the other figure. That was better, I think. Okay. So when they are aligned, you have when they are exposed, you have flow. Okay, you have very little delta P. When they that's not a nice picture. Let me see if I. Okay, this is a better figure. Not sure where in which brochure is that. Okay, so you see, with this one you regulate the number of holes that are exposed. Okay, if you close more holes, then the fluid can pass through less holes, and then the pressure drop will be higher. And if this goes all the way up, then you have all the holes are uncovered. Okay, so that's called a cage type choke, which is very much used probably for the coral field. They are going to use a choke like that. See, sometimes you have to go to the notes from. Okay, wheelies or disc or rotary disc choke, and this is a cage, and this is pretty much used subsea, and it's used for one reason. It has a very nice durability. Okay, because one of the problems with the choke is when you like when you do that, you create a jet, okay? When you pass the fluid through a very small opening, you're essentially creating a very strong jet at a very high speed. And that creates a lot of erosion. That jet, no matter where it hits or where it's going to hit, is going to create erosion. Erosion with the walls, erosion with everything. Okay, so it's a huge amount of pressure. What they do with that design, with the cage, is that basically they're using that energy against each other. You see that the holes, they are placed in front of another, such that if you have this jet of high speed, they hit each other and then they go down. They lose all the energy by hitting each other. Okay, so that's called a cage choke, and that's very popular, but it's very expensive. So you have to use it for reach, for uh, that's called cage choke. Okay, so we have to care for some things. So the main function of the choke, like I mentioned before, is to dissipate energy. Okay, that means to reduce. However, that's something is easier to say, but it's sometimes difficult to achieve. Okay, so there are a few things that we have to, so a few, a few issues, okay, that we have to cite. So when the pressure is reduced, okay, this can induce, if we are in an oil, okay, this can induce gas vaporization. Okay, gas will come out of solution because you're just lowering pressure dramatically. And if you have gas, that can create liquid condensation. Okay, so you will have multi-phase flow. The biggest problem is that you find actually erosion. Okay, you can cause very strong erosion in all the components that you have high velocity. Okay, high fluid velocity. And moreover, due to that geometry, if you have some sand or if you have some particles on the flow, that causes also a lot of issues. Okay, that can cause even more aggravated by erosion. Okay. One more thing that you can have is that it causes, and we will see now, you're going to do a short exercise. So in gas, it causes cooling. Okay, because when the pressure drops dramatically, also the temperature drops dramatically. And sometimes it can cause more liquid condensation and what can cause the temperature, such a low temperature? Some things that we know already, we know hydrates, right? And it can cause also ice, okay, even the formation of ice. So that can lead to a block. And another thing that also happens is cavitation. You know what cavitation is? Yes? Okay, so I don't show you the video. Okay, is close to the wall when you have this vaporization. That's a liquid. The pressure sometimes lowers very much. So then you have vaporization, and then it passes again through another area with high pressure, and then it condenses again, and it causes this jet stream that heats very much and takes material out of the wall. So you can have all of those issues in chokes, okay? And typically, if we look at, so we are going to represent a choke. Every choke has different geometry, right? It has different weight, it has a needle, it has all kind of things. But we can represent generically choke has a restriction, okay? Because you basically have, always you have a big channel that ends up in a very small channel, and then you have an expansion, okay? So that's essentially a choke. You have a channel where you have a lot of convergence of the fluid is deflected very dramatically to enter into this small channel, okay? Then you have an area with high velocity, extremely high velocity, and after that you have another area where you have an expansion, but you don't have that much pressure recovery. That's the intention of the choke, okay? You don't have that much pressure recovery. So if we plot pressure along the x-axis here, you'll see that initially you have a high pressure, and then when you reach the drop is extremely dramatic, okay? Then it's going to recover slowly, 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 and almost doesn't recover. In the expansion area, maybe you have some recovery. Let's make it, you have some recovery, but it's not very much, okay? So the pressure you have at the throat, in this is called the throat of the choke. How do you write throat? I think it's like that, right? Throat, okay? The pressure you have in that region at the throat, okay, is more or less is not recovered due to the length of the choke. Okay, it almost doesn't go up. And this is what I was saying, that you might have sometimes, here is the pressure vaporization. If you have oil, or if you have gas, will be condensation. It could be the pressure where you have hydrate formation or you have icing. So that can be, it will happen because the pressure actually is not exactly, let me make a better drawing. This is much sharper, okay? This is not so, this is much closer. Something like that. Okay. So you have here a minimum point where the pressure drops and then recovers through the whole part of the choke, and then it continues. You have very little recovery in this diffuser. Okay. So now let's do just one thing. Okay. I hope I brought enough. One more? Yeah. Okay. So that's just to show because we are saying that the temperature, it causes cooling, okay, if we have a gas. And we are going to work mainly with gas, okay? It's not so exciting, the joke with liquid. So let's, what you have now is, the pressure enthalpy diagram. I think that's called well, when it's for water, it's called the Molière diagram. Okay, let me put it a bit smaller, okay? Okay, so that's methane. And we know in reality, production gas is not 100% methane. Okay, it's a mixture of different gases. But as a first approximation, I suggest we use methane because it's very easy to see interesting things with methane. Okay, with just pure phases. So, how is the expansion on a choke? If you were going to characterize it from the thermodynamics point of view? Is it constant temperature? It's not constant pressure, right? So if you remember the energy balance that we make on a valve, right? We say, how does it go? Energy that comes in, which is mass flow times the enthalpy, right? And the enthalpy 1, enthalpy 2, minus enthalpy that comes out should be equal to Q, the heat, minus W, right? The heat exchanged by this control volume minus the work. And in a choke, luckily, I don't have, this one is very small because it's very short, and this guy, I have no work here, okay, outside of this control volume. So that takes you to the conclusion that H1 is equal to H2, that the expansion on a choke is isenthalpic. Okay, so let's use that. That's why this diagram has enthalpy. Okay, that's why it's not I chose it randomly. That's why it has enthalpy, because you know that the point where you start, you're going to go from 1 to 2 with the same enthalpy, just like in a vertical line. So let's do it for that case that we discussed in class, okay, the second day, that we said we had. Okay, so let's remember, what did we have? Okay, we have pressure in of, that's like 190, okay, let's say 190 bar. Okay, so let's say P1 is 190 bar. The temperature, I think, on that well was I think was like 90 bar, 90 Celsius. And P2, how much was P2? We have it here. P2 was, yeah, in this case was 40 bar, I think. Okay, 40 bar. So let's try with those points. We want to find out how much is T2. Okay, what is the temperature at the discharge of the choke? To see all kind of things, maybe we have hydrate, maybe we're going to cause cooling, maybe we're going to have, because it gets too cold, the choke, I will have accumulation of ice, okay? Ice build up outside of the choke also. So I just want to see if there are any consequences due to that. So let's find the point in this diagram here. We know enthalpy is on the x-axis, okay? Pressure is here. So pressure we have is 190 bar. How many megapascals is that? 19, right? 10, 0.1 megapascal. That's 0.1 bar. Yes. Let's take the calculator. Pressure, we want to go from bar to megapascal, and we say we have 190, 19, okay? 19 megapascal. So remember, that's logarithmic scale, okay? So we have that 9 is closer here, someplace here. 1, this will be 20, right? 20, 30, 40, and so forth. And here you have again 11, then will be maybe 12, 13, blah, blah, blah. So 19 will be someplace very close to 20. Okay. And the temperature we have is 90, right? Okay. So the temperature, you see the lines of temperature. The lines of temperature are like that. Okay, temperature 50, 0, 25, 50, 75, no, sorry.
100.
Temperature, they are these lines, okay? The lines that go like that, and they do like an S shape. So where do we have 90? This is 100.
This is 100.
This is this is 50. This is 75, and this is 100. Okay, so we have to knock this line that comes up with 20. So can you do it? Just do the mark there. I will try to do my best here. 100 and knock it with 19. Yeah, that will be my point 1. Yes? You found it? The temperature is usually below the line. Okay, so this line, which is above here, that's temperature 100. This line that is above here, that's temperature 50. No, sorry, it's above the line. So it should be this one. This point here. Is this point here. Okay? T100 is above the line, so it's this line that comes here. If you need more paper, if you made a mistake, there is some more here. Okay, what is the second point? So the second point is 40 bar. 40 bar is how many megapascal? 4, right? So this is 1, 2, 3, this will be 4. So it's going to be on this line, okay? But we don't know the temperature. But we know that the enthalpy is the same, right? The enthalpy is the same as 1. So we just move vertically until we find that point. Okay, point number 2. And now you can read the temperature. What is the temperature of that point? T, I'm getting... It's like 65 maybe, right? No? 50, I think this is 60, 70, 80, 90, 100. Okay? So let's see. This is, let's see if I'm not making a mistake. This is 100, this is 90, 80, 70, 60, so it's between these two lines. Okay, 65. So you see that the temperature dropped from 65, not much, okay, like 25 degrees Celsius. But exactly that's what you have to do when you have a real fluid. Okay, you have to calculate how much delta P you want, calculate the expansion, and be careful if you don't have any problems. Okay, so that's regarding the temperature behavior of the choke. Okay, in temperature sometimes can be very important, and just keep in mind how do we solve temperature. Now let's go with the most important thing that we normally want is Q versus delta P. Okay, like all of our IPR, ITPR, the intention was to find Q versus P, okay, versus delta P. So let's make an experiment, okay, where we have, or a thought experiment, where we have here P1 and P2, and we have some rate, okay, and this rate will be the rate, let's say that that's gas, okay, this experiment will be done for gas, and is at standard conditions rate. So let's try to plot okay, keeping P1 constant. What happens if for rate 0, okay, how much will be, let's say that this is delta P, which is P2 minus P1. Okay, P1 is constant. Okay, for 0, how much is the delta P? 0 rate? 0 delta P. Okay. Then I start to increase the rate. Okay, let's say how will the trend be? Will the trend go? If I start to increase the rate, now I'm flushing more rate, how will P2 be if I increase the rate? Okay, the pressure drop, you have a non-linear pressure drop, okay, which is something like that. It has it's like a parabola, okay? And you can see that if this pressure is constant, to get more rate, I have to lower this pressure. Okay, therefore the delta P has to be bigger. Sorry, this delta P is not P2, but it's P1 minus P2. Okay, or equivalently, if I have more fluid flowing through the choke, the delta P will be bigger. Okay, so, yes? P1 minus P2. Well, it's Friday, no? I'm allowed to have some mistakes. But good that we have sharp people looking. P1 minus P2. Okay. Okay. So that's going to increase, but it's not going to increase indefinitely. Okay? It's going to increase until it reaches a point, a very important point, and this is crucial for understanding choke. At that point, what happens is that the velocity of the gas at the throat, okay, is getting very, very close to the velocity of sound in the gas. Okay, this A, which is sound velocity in the gas. Okay, you remember for air, how much is the sound velocity in air? In air is 300 around meters per second. Okay, so it's quite high, and if you have a real gas like methane, this A is, you know the equation is K, where K is Cp over Cv, RTZ divided by molecular weight. Okay, so you can calculate, but it's going to give you a number similar to 300. Okay, I think we did the experiment for methane. Yeah, I think I have here some numbers. So for methane, for CH4, the A gives you around 542 meters per second. Okay, a very high number. Okay, 1.6. T is 80, and M is 16. Okay. So when the velocity exactly at the throat is equal, what happens? You reach critical conditions, right? What is called critical flow. So, okay, critical flow. What happens when you reach critical flow? Below, in any point here, right? Let's say I was fluctuating this pressure, some reason. Okay, I could fluctuate due to the separator. I was controlling to go up and down, up and down. In all of this range, if I fluctuate here, this one will also fluctuate, will also feel the change, because the pressure change, they propagate at this velocity, 542. Okay, but when I reach, the velocities are the same, the pressure tries to propagate up, but it cannot pass through the throat because they go at the same speed. So any perturbation that travels up very fast is going to get swept. So it doesn't affect at all the downstream conditions. So that's what is called critical flow. So below that, so if I try I won't be able to flush any rate greater than Q critical. Okay, QG critical. Okay. No matter how I lower P2, if I put it to vacuum, if I lower it very much, I won't be able to pass just because the change that I make here in pressure doesn't reach P1. Never, because the velocity is so fast that it doesn't allow the pressure change to propagate here. So it doesn't matter for P1 is the same if you had this P1 critical, P2, okay, or if you had this P2 here, for it will be the same because it doesn't see any change in pressure. Okay? So that's how the curve of the choke looks like. Okay, delta P, the Q, I increase the Q, the delta P is also increasing, which makes sense. Okay, but after a point, I reach the critical rate, and then it's just a vertical line. Okay, this point happens when approximately when P2 over P1 is very close to 5 or 55. Okay, that means if I substitute on my expression P1 minus P2 delta P, and then I say now that P2 is P1 55, right? I'm going to get how much is that? P1. Okay, so I'm going to get exactly at 0.45 P1. That here? And the way, so how do I find exactly that number? I can use that approximation, but in reality, in gas, I can, so for those of you who took compressible flow, P1 over P2 critical is equal to 2 divided by K plus 1 to the power of K over K minus 1. Okay, where K is the ratio between Cp and Cv. If we want to know exactly where it happens, we have to use K and we evaluate that expression. If not, rule of thumb is around 0.55, 0.6, that's when this happens. Okay, now there comes a difficult question. Okay, what happens if a tricky question. I have again my same plot, delta P, and I have is going up like that at this point. So what happens, that is for this orifice, okay, for this size of choke. What happens now if I use a smaller choke? Okay, that's for number 1. Okay, what happens for number 2? How will the curve look like? Okay, the two will depart from the same point. When I have no flow, they depart from delta P equals 0, right? But now, if I try to flush the same rate through the small one, okay, it will give me a higher pressure drop. Yes? Okay, so the curve for this is for 1, and let's paint it for 2 like that, in red, is going to be something like this. Okay, because you're going to get a higher pressure drop for the same rate. Okay, now when I'm going to achieve critical conditions, here I'm keeping P1 constant. Okay, P1 is constant. Well, you know that critical conditions happen when delta P is 0.45 P1, right? And P1 is the same for both cases. So the critical conditions happen at the same delta P. Okay? The only difference is that for the small orifice, I reach the critical rate much faster than for the big orifice. Okay? Okay. Now, in the time we have, I'm just going to show the equations that we are going to use. Okay? We are going to exactly, tomorrow, we are going to reproduce this plot. That's how the choke behaves. Okay, you have a critical region. So that will be the critical region. No, sorry, the subcritical region. And here it will be the critical. Okay. Oh, something that we forgot. What happens with if the pressure P1 changes? Okay. So that's for, let's say, let me just make the note here, Phi1 and Phi2. So that's for Phi1 and Phi2. So what happens if P1 changes? Okay, let's make again the same plot, dP, QG. I have here for 1P, P1. Okay, and now let's use another P1 star, which is P1 star is higher than P1. Let's say first, where will the critical delta P occur? Okay, delta P, you know, is 0.45 P1. If P1 is bigger, now it will happen at a higher delta P. Okay, so delta P, so let's move it here. It is delta P. This is delta P critical for P1, and we know delta P critical for P2, it will be higher. But the curve will be to the left or to the right of the original? To the right. Why to the right?
Because the backflow won't be allowed to go beyond that limit, because the flow that is coming from P1 is much higher than the previous one.
Yeah, let's say we're using the same flow, okay, QG, here. Is the curve going to be like this, or is the curve going to be like that? On the left. Sure? Do we leave it for homework? Do we leave it for homework for tomorrow? In the class. Yeah. Yes. The pressure loss, right? This, at least in this region, okay? The pressure loss depends on the velocity that you have, how big the velocity is, okay? And the velocity, you know, it's so it's QG, the local, QG times BG, which is a function of pressure. So if pressure, this pressure is higher, okay, P a star is higher, how will the local rate be at the inlet of the choke? It will be lower, right? If the pressure is higher?
Yes.
Yes? If you remember, how is the curve for BG? BG versus P. So if the pressure is higher, let's say we're assuming we have a higher pressure here, okay? Then the local rate will be lower. Yes? The local rate is lower, the velocity is lower. If the velocity is lower, the delta P has to be lower. Yes? One more?
Lower rate implies high pressure.
We are saying now the same local rate, okay? For the same local rate, okay? We are looking now at the inlet of the choke, at P1, okay? We say for P1, we have this curve. Now for P1 star, which is higher pressure, we're going to have a higher local rate. Yes? Okay? If we have a high, no, we are going to have a lower local rate. Because you have a higher pressure, Vg is going to be lower, and then this local rate will be also lower.
What's the relation between rate and pressure?
No, it's just to know if the curve, there are two choices. One of them is that the curve is like that, okay? Or one of them is the curve is like that. And we can make a bet here. We'll have 50-50. People say, is the one to the right, is the one to the left. I'm trying to get some indication which one is it, okay? So I'm saying the delta P, okay? My reasoning is that the delta P across the choke, okay, is a function of the velocity of the gas, okay? More or less, it's a function of the velocity of the gas in the choke. Now we know the velocity is going to change, right? It's going to be increased dramatically. But now I'm going to say the velocity of the gas at the inlet, okay, at 1, in point 1, will be the local rate of 1 divided by the area of 1, right? Okay. Now, the local rate for, and the pen is neglecting to work. So for P1, the first pressure, the red one, QG1 will be BG at P1 times Q's standard conditions. This is constant, okay? We're looking at the same QG. Okay? Now, for P1 star, which is bigger than P1, QG1 star will be BG at P1 star T times QG, which is the same. But we know that BG for P1 star is smaller than BG at P1 T1. Okay? Therefore, QG1 star is going to be smaller than QG1. And therefore, BG1 star will be smaller than B1, okay? And therefore, delta P1 star will be less than delta P1. Okay, because the velocity is smaller, therefore, the choke delta P will be smaller. Therefore, the curve that we have to use is the one to the right. Okay? Because the delta P is lower than for P1. Hmm? Delta P. Okay? You have to sleep. Either how we can argue, calculate, you can say yes, no, yes, but when you make the calculation, you see the result. Okay? So we will try to make the calculation. But it's just to give you an indication. It depends on the velocity, and the velocity in this case will be lower just because the pressure is higher. Okay? P1 star is higher than P1. Hmm? Hmm? Higher pressure, lower local gas rate, and lower velocity. Okay? If I have a higher pressure, it's gas. It will tend to compress, and it will take less space in the pipe. Okay, easy exercise. We have done the first day, I think. Okay. Okay, if you remember this case that we did, if the pressure increases, the velocity decreases. Yes? And because of that, there is less velocity at the inlet of the choke, the velocity of the throat will be smaller, and the delta P will be smaller also. Okay? Yes?
Can I use the formula QG as a constant? The QG local is a variable and BG is a variable as well. Like if I increase the pressure, BG will be lower and QG local will be higher.
No, when this one goes down, this one also goes down. Okay? Because this guy is constant. We are looking now, we are just looking now at this, the two, the same, this one and this one, they have the same QG. Okay? So that's why this guy is constant. If this goes down, this goes down. If this goes up, this goes up.
I understood the reaction, but I'm having no problem with the representation here. Could you slow down? Yeah. You're saying that what we show in the chart is the constant QG.
Yes, but that's local rate, standard conditions rate.
The one that
This one is standard conditions rate. It's like mass flow. Okay, this is local rate, which we are not plotting any place here, but I'm saying that the local rate affects the velocity. Okay, so that's why if we look at the local rate, it tells me something about the velocity, and velocity tells me something about pressure drop. Okay? Don't be confused if this is not really that important. If you can make the calculation, you can verify your numbers. Okay, that's what is important. So we are going to look at that on the exercise. So just again, like for the IPR, like for the tubing, I have to show you, you have to see it once in your life, okay, how the choke equation comes from. Okay? And the choke equation comes essentially, okay, derivation of the choke equation. And we are going to start with liquid. Okay? Okay? And all choke equations, or most of choke equations, they are based on making a balance between two sections. Section 1, which is the inlet of the choke, and section 2, which is the throat. Okay, usually you are taking these two conditions. So for that we apply, this Bernoulli equation. Okay, saying that because they are so close one to the other, you have almost no friction. Okay, so you say, what does it say? Bernoulli equation, dP, okay, will be equal to, I think I have a better density, velocity, du, right? This will be equal to 0. Okay? These two, actually, you have here the dl and the dl, okay? But because it's equal to 0, we can get rid of the dl, okay? And here, neglecting friction and neglecting what else? Yeah, the friction, that's friction, right? Neglecting friction. And I'm also neglecting the change in elevation, right? Should have three energies. I should have pressure, I should have kinetic energy, I should have elevation, this potential energy, and then I should have friction. I'm saying the inlet 1.1 or 2, they are so close that there is no difference in elevation, and they are so close that the friction is almost negligible. Okay, neglecting friction and neglecting elevation change. Okay, and then I apply my snakes. Okay. Okay, from one point to another, from point 1 to point 2, from point 1 to point 2. And I should put this density with pressure, okay, because in case it depends on pressure. So I have P2 minus P1 will be equal to density, and this gives me U1 minus U2 squared divided by 2. Right? Correct? And I'm saying that density is more or less constant with pressure. Okay, I have almost what I need. Okay, I have here, I can get a rate from here, and I have here my delta P that I wanted. Okay, but I need to correlate these two velocities. Okay, so for that I use the mass conservation equation. Let's say that U1 times area 1 will be U2 times area 2. Then I say that U1 is, oh sorry, A2 is pi d squared over 2 over 4, and this you have pi 1 squared over 4 times U2. So this, they cancel each other, this pi and this 4, and I end up with phi2 squared over phi1 U2 and U1. But really what I need to substitute in this equation is actually U squared. Okay, so now I squared both sides, and I end up with U1 okay, and this factor, the ratio between the diameters, I call it beta. And that's a factor you're going to hear very commonly in chokes. Phi2 over phi1, that's called beta. It's a value always smaller than 1, and then you end up with U1 squared equal beta to the 4th U2 squared. Okay. And now I substitute in the equation, substitute in the Bernoulli equation. Yeah, and I end up with P2 minus P1. It was P2 minus P1, right? Yeah. Equal to density of the liquid times 0.5 beta for U2 minus U2 now I can take U2 as a common factor, P2 minus P1, 2 here, then I have beta minus 1, okay, and finally I end up with this equation, which is the square root of, and we are going to make it positive, okay, so we say P1 minus P2 divided by 1 minus beta 4 2 over the density of liquid. So we are almost there on the choke equation we want, but remember the choke equation, usually we want the Q, okay, of the liquid as a function of delta P. Okay, so I have to change now to convert from velocity to rate. And so I say U2 times the area, that will be my rate, okay? Assuming this equation is for, not for oil, but for ideal liquid. Okay, that means not compressible. Okay, if it was compressible, we will have to add also BO, okay? So if it's ideal, we should, so BO is equal to 1, right? Otherwise, we should have to Q liquid. And then we substitute QL will be, sorry, QL divided by area 2 will be U2. And then I substitute that here, QL is equal to area 2 okay, and that's the choke equation. If you have a non-ideal liquid, then you have to use, actually you say QL is equal to Q oil at standard conditions times BO, and that should be measured at P2, T2, U2, A2, and then that gives you that U2 will be equal to QO, BO at P2, T2 divided by A2, and then you can substitute in the same way. Okay, but liquid we are not going to use very much, so don't be worried about it. That's the equation we have to use. Now, there is one thing, that equation out of the box doesn't work very well. Okay, and there is a reason for that. If you look at exactly at the throat, okay, point number 2, when we are doing our analysis, here the flow is flowing usually through the whole area. Okay, so A1 is a good approximation. But when we look here, due to this effect of contraction, okay, the fluid normally doesn't circulate through the whole area. Okay, it's going to circulate through a reduced channel. How do we call this channel? Back in your fluid dynamic times, fluid mechanics, vena contracta, right? You heard that name, the vena contracta? Okay. So it doesn't flow through the whole area. It flows only through a section of the area. So what people do is they stick on this equation that I have here, and wow, it's time to finish. Okay, so they come on this equation 2 delta P rho L 1 minus beta to the 4th. They stick a constant to change that area, to make it smaller. So usually that CD is a number, CD is less than 1 to account for vena contracta. Okay, so ladies and gentlemen, this is the choke equation for liquid. I have now a relationship between Q, okay, and delta P, which is, if you see, it's like delta P is equal to a constant, right, times Q squared, which is very similar to this region here. Okay, it's very similar to that region. It's like a parabola. Okay, and I use that equation with that CD. That CD is something I have to measure. It will depend on the choke. Okay, this CD depends on the choke model. Okay, and I say, remember, usually I cannot measure pressure here. Okay, I cannot measure pressure exactly at the throat. Okay, I just measure pressure at the inlet and at the outlet. But if you remember that this, where was it here? Okay, the recovery of pressure after the throat is very, very small. So they say the pressure that you measure here is essentially going to be very similar to the pressure of the throat. Okay, so that's why I measure here, and I apply the equation here and here. Because they say the pressure really doesn't recover much. That's the intention of the choke, so I have almost no recovery. Some people try to make that equation better by saying, well, the pressures are not exactly the same. Okay, so I say, so one assumption to use this equation is that P2 is very similar to P at the outlet of the choke. There is negligible pressure recovery at the choke exit. Okay, finish. That's how I use that equation. If I want to use compressible fluid, I have to include the BO, and then the equation ends up being for, let's say here, for real oil, I have to add the BG, so Q oil will be A2 CD BO P2 T2 square root of okay. We are not going to use it much. It's not very interesting for, we normally don't have chokes with operating just liquid, okay? At the conditions of pressure of temperature at the wellhead, usually we have either single phase gas or we have two phase. We normally don't have oil, okay? So that's why the choke is interesting to see, because for gas, we're going to do exactly the same. We're going to do exactly the two same points, okay? But now the density, always gas is a bad guy, okay? Density now, you cannot integrate because the density is not constant. So you have to find another trick how to do it for gas, okay? But it's very interesting, it's exactly the same process from one to the vena contracta, and then correcting by the area. We know it's not circulating through the whole area, but just a fraction. And we stick a constant in there. Okay, we are done, 30. Any question before we close? Yes?
So, with choke placed in the regulating system,
When the choke is placed in the system, it's just downstream the wing valve. It's downstream the wing valve. You remember our, okay, remember our well, we had lower master, upper master valve, wing valve, swap valve. The choke is normally here, okay? So it's after the wing valve. Okay, thank you for coming. See you tomorrow. We have a session tomorrow.